Awesome. Well, thank you for joining us. My name's Itzel Torres, and I'm working with our 3C Run team out of Ventura County. Today we have Mechanical Systems in Detail with Ken Levinson from the Passive House Network. Before we get started with him, I just have a few housekeeping slides that I'll go over. And for anybody who's new to 3C Run, just a little bit about who we are. Next slide, please. By now, I know all of you are pretty familiar with Zoom, but we ask that everyone make sure that they are on mute when they log in. And if you want to verbally participate, you can use the raise your hand button and we'll get to you. Or we also just invite people to ask their questions in the chat and we'll make sure that gets answered. Next slide. A little bit about 3C Run, the Tri-County Regional Energy Network. It is funded by ratepayer dollars that we pay into our utility bills through the public goods charge. The benefit of ratepayer funded trainings is that all of the dollars go back into our local economy and free trainings that I think we try to tailor to the building industry in our region. Next slide, please. 3C Run currently has 6 programs focused on 3 services: incentives, training, and technical support. So for our incentives, we have our home energy savings program that offers single family and multifamily incentives. And then we have our commercial program as well that works similar to our single family, but for commercial buildings, and we'll help folks get connected to those incentives. And then we have our building performance training program, which offers trainings for building industry professionals, a lot of them focused on building science. We have our Energy Code Connect program that offers also live and on-demand trainings, specifically for code and navigating Title 24. And then for our technical services, we have our Agriculture Energy Solutions program that offers technical help for high energy use farmers, and it helps them cut utility costs and connect them with rebates. And our Energy Assurance Services program is customized energy audits for critical facilities focused on resiliency in our area. And with that being said, I'll hand it over to Ken to get us started with our training today. Thank you.
Great, thank you so much. Good to be here to talk about Passive House and their mechanical systems in detail. My name is Ken Levinson. It's good to have you all with me. I definitely see some familiar names and look forward to going through this. Please, as we go through, put any questions in the chat. I'll try to get to them as we go. If something comes up that is really critical to understand, or if you don't think I've fully fleshed it out, please raise your hand, I think, and we can unmute you and you can speak up, or just keep at me in the chat. I'll make sure I get around to it. We have a lot of material to go through here in the next 2 hours. I will try to move through pretty expeditiously. So if I am jumping a little too quickly, feel free to also tell me to slow down. Briefly up front, the Passive House Network. If you aren't familiar with us, we're a 501c3 nonprofit. We are nationally focused. Part of the International Passive House Association, focused on the United States, in affiliation with the Passive House Institute, and really focused on capacity building, on education, on training, on connecting people to peer-to-peer knowledge sharing. We work with the North American Certifiers Circle, a group of Passive House building certifiers, and happy to actually see a certifier. Tad Everhart is on the call here today. So maybe Tad, you can help me out if I get stuck. I want to briefly mention before we get started, our design competition that we launched earlier this year called California Rebuilds. In response to the needs in Los Angeles after the Eaton and Palisades fires in particular, and trying to innovate, inspire, and inform folks in terms of what is possible. The deadline is later this year, and we're doing a series of events around that. We had one earlier this week on Fire Rebuild with Mike Horgan at Cairn Collaborative, who I know is an instructor at 3C Ren sometimes. And we're doing a series of other trainings too. We're going to be doing Easy pH training on July 24th, which is a simplified version of the energy model for Passive House. So be sure to check that out. And the last training bit I want to just mention here is we are kicking off our summer cohort next week. I can't believe it, July 1st. And there are all sorts of incentives. I know 3C Ren has some very generous incentives that can be available if you're in California in general. If you're in Los Angeles County, we have some specific incentives, but for folks across the United States as well. So be sure to check those out. Today, we are going to look specifically at the mechanical systems and how are they working with Passive House and complementary strategies, going through the methodology, the parts and pieces, and process along the way. So I like, as was kind of asked earlier, tell us a little bit about yourselves, if you don't mind, where you're located. I'm guessing many of you are from California, but we do get people from across the United States, and it's always interesting to know. What's your job or role? How are you coming from to this, working with the projects, whether you are today or hoping to in the future? If you don't mind dropping that information in the chat as well. Great, Irvine, California, mechanical engineer. Thank you, Brandon. And how familiar are you with Passive House? Passive House designer, Santa Barbara, great. Yeah, getting those projects is the lift, and that's a whole other talk. But great to see you out there. Not familiar. Okay, Brandon, good. Always want to have new people. And yeah, good to see you here, Tessa and Tad. So I know we've got a full range of people who have exposure to Passive House, so we will be touching a little bit on the basics and make sure we bring everybody along. But we will be jumping through it pretty quickly and diving into details of the mechanical systems. Great. Thank you so much for everybody's letting us know. Wonderful. So a couple of words about myself. I am an architect by background. I practiced for a couple of decades. I am based in Brooklyn, New York. I started Passive House in 2010 about, and was very fortunate to have a client early on when I discovered Passive House agree to, when we did the gut renovation of their townhouse. So this is a pre-Civil War townhouse, a good old building in Brooklyn Heights, New York. We did a gut renovation to Passive House standards. And it was an eye-opening experience. And for the reasons why I was coming to Passive House principally were around climate activism and carbon emissions. Where my clients came to it, though, through our conversations, was through comfort and health, safety, resilience, and kind of future value of the property, future-proofing the property. And so having those conversations and everything was quite interesting and kind of set me on my passive house journey in many different ways. I'll probably refer back to this project in a couple of different ways going forward here. Great. So the agenda for today, want to speak briefly about the context of passive house, because passive house is kind of, it's not literally anti-mechanical systems, but it is focused more heavily on the passive aspects of the building, hence the name, and not so much the mechanical systems. So we want to make sure we set the table well, and then we'll talk about the mechanical systems and getting into the strategy of it, and then go into some of the component parts: ventilation, the heating, cooling, domestic hot water, other systems, solar. We'll have some case studies, and there's a resource list at the end. We will be primarily talking in the realm of single family and multifamily as well. If you have specific questions on other use types, we could try to address them, but we're keeping it really, really within the domestic residential kind of parameters. So we'll see. Brandon, good question. So passive does include natural ventilation, but it's not exclusively natural ventilation. We'll get into that for sure. So passive house. So really what we're talking about is an enclosure first approach, right? That enclosure that is keeping the weather out, keeping the inside comfortable and healthy, is a really important driver of the performance of the building. It's the architecture of it. And passive house really forces us to put the architecture first, whether it's, Palladian Renaissance architecture or modern architecture or some vernacular architecture. We're really embracing that fabric of the building. We want the architecture to drive performance and not just rely on the mechanical systems to make up for poor performing enclosure. So that architecture is going to really help us maintain the healthy indoor air quality, make the space cooling and heating much more efficient. And of course, we want efficient hot water as well, although that may not be so driven by the architecture. We're going to reduce emissions. And, this idea of net zero, we want to balance demand and production of energy. Passive house really is super helpful in kind of sorting through the static of construction. There's so much going on in construction. What really matters, what really drives the performance. And it's often lost on folks, even folks that do know better, but just in the day-to-day of it, one can get disoriented. So passive house keeps us focused on fundamental elements. I consider it kind of like cooking. And this wonderful book, Salt, Fat, Acid, Heat, which says, let's focus on these core elements of cooking. And if you master them, you can be a great cook and make great meals. And you don't necessarily need to know everything, and you don't need to have the best ingredients necessarily, but you know how to manipulate the food and have a great meal. Passive house is doing that with building elements. Wolfgang Feist, who really kicked it off and founded the Passive House Institute, says in this quote, "I was working as a physicist. I read that the construction industry had experimented with adding insulation to new buildings and that energy consumption had failed to reduce. This offended me. It was counter to the basic laws of physics. I knew that they must be doing something wrong. So I made it my mission to find out what and to establish what was needed to do it right." So here we see Wolfgang seeing the construction industry adding one of these ingredients of high performance and not getting any results because they weren't really focused on how to bring the things together. And so passive house connects the dots. I want to briefly just note some passive house resources as we dive into this. You will have access to a PDF of this presentation. You don't have to worry about taking extensive notes or anything, and the links and whatnot you can look up after the fact. But we have a building database on the Passive House Institute website that is very full and rich of information, all different types of projects, lots of details, information about who is involved in the project, the systems involved, great resource. There's a component database of certified components for critical components that we'll talk about. And we've developed a manufacturer directory on the Passive House Network website, where you can look towards these different areas of critical aspects of Passive House construction and find manufacturers that are either providing certified components to the American market or are providing what we call Passive House compatible components to the American market and are active in the American market. So when you start out, years ago, there were like 5 window manufacturers. Today, there are dozens of window manufacturers that you can choose from. And you don't have to reinvent the wheel. Come to the list, see who's there. If you know of somebody that's not there, please let us know. And we're looking to expand it. It is a curated list, but it's not pay for play. It's anybody that qualifies is going to be welcome to be there. Finally, some books. There are other books and briefs and pamphlets, slide decks. We are finalizing a page on our website about this, but here are some you could come back to and look up, talking about the details. Regarding mechanical systems, probably this one by Allison Bales, which is not a Passive House specific book, is the most applicable. These two on the right are more straight building science books, but very complementary in terms of what we're trying to do. So back to what we're doing with Passive House. So, one of the things that was really interesting with my original clients in that townhouse was I was coming at it from the energy efficiency point of view, the carbon emissions point of view, the climate mitigation point of view. My clients weren't, but efficiency, which I think is pretty, well known that Passive House is very focused on energy efficiency. It really underlies all these other things that we value. So this idea of comfort and indoor air quality, quietness, resilience, affordable operation and maintenance, all of these things, energy efficiency is the foundation for. From the owner's side, we can do this affordably. It may not be at cost parity. It's going to cost a little bit more. It's high quality construction, but it should be manageable. We're going to end up with fewer callbacks. We just had Mike Horgan talking on PHM Presents on Tuesday, how he gets no callbacks on his buildings because they're putting them together very, very well and focusing on those drivers. Reduce maintenance, perpetual energy savings. We talk about payback and simple payback, but realize as energy spikes go up in the future and becomes more expensive, you are going to get that savings year over year over year. And by crushing that energy demand, you're really insulating yourself in terms of economic security going forward. We see Passive House delivering and holding buildings at the top of the market. It's hard to know exactly where it lands when we have an overheated real estate market, you have a housing shortage, but we're creating durable, high quality asset. And at the end of the day, what we see is that developers and owners who are pretty savvy about this stuff, who may initially see it as a higher risk investment because it's new, it's different. What is this? Ultimately realize that all of these things are contributing it to being a much lower risk investment. Kind of crazy not to do it. I want to mention a couple of things in terms of the qualities of this that we talked about. Wildfire resilience is obviously a big issue, and it's not a driver, prime mover of Passive House, generally speaking. But what we've found is that many of the attributes of Passive House do help support a more fire resilient home and building. And particularly, um, you know, the simpler form, continuous insulation, air tightness, the high performance windows, the ventilation, we'll get into all of that. The air tightness, I think, is the top of it, and many people in California now are calling it smoke tightness. And we have a climate disaster support page, and of course the competition underway. This article just hit the internet yesterday, I think. Maybe the day before. I'm assuming it's coming out in the Sunday New York Times, called "Unsafe to Inhabit: The Toxic Homes of Los Angeles," and it's a devastating survey of the homes that survived the fire. Didn't burn down; they were intact, but they are full of poison. The smoke carried into the homes, lead, cyanide, formaldehyde, carcinogens. Um, and it's a bracing article. I encourage everybody to Google it. Don't read it now, read it after today's talk. We'll be doing a post on it next week. But definitely, whatever we can do to keep the smoke out is going to help our resilience, whether it, burns down or not. So Passive House, again, this idea of efficiency supporting greater comfort and health. This is kind of the secret sauce of it, that they realized that we could formulate the approach to the building science where efficiency actually contributed to a better life. It's not about sacrifice. It's about being healthier and more comfortable. And yes, when the power goes off, if it's cold out, you can stay warm and comfortable without the heat for extended periods of time. You can sit by the windows on a cold winter day and be comfortable. We can apply this to homes in all climates. We can apply it to multifamily buildings. We can apply it to recreational buildings, public buildings, firehouse, certified firehouse on the right in Vancouver, university buildings, public school buildings. We can use any kind of construction type. You want to build in wood? No problem. You want to build in concrete? Passive House can do that. Steel, no problem. Really, there are lots of different ways, and you could have different agendas that you're bringing to the construction project. Passive House can work with those. It's not dictating specifics like that. You can just take how you build and how you design and essentially tweak it and just make it a bit more rigorous based on these Passive House principles. So one thing I think people will strike them sooner, probably sooner than later, is that a lot of what we talk about in Passive House is just basic building science. It's like, really, this is just pretty straightforward in terms of the building science, which is true. But what it does, again, is it forces us to rigorously apply them. Like, using salt on our food and heat on our food is pretty basic. But if you can manipulate that smartly, you can have a much better meal. So this is the same thing with these 5 principles. Of course, it's a bit more complicated. We'll get into some of that. But at the outset, continuous climate specific levels of insulation. So if you're in a cold climate, you want a heavy parka on, and you want to be really wrapped up good. If you're in a more mild climate, maybe you just have a sweater and a windbreaker on, or you have a sweatshirt on or something, but you don't want to wear the sweatshirt in the parka climate. And that's the way our conventional construction is, typically. We want that continuous insulation to be thermal bridge free connections. So really, continuous insulation is continuous, typically at the joints between walls and floors or window installs or where structure comes through, we have interruptions to the insulation, which can be detrimental in many ways to the performance of the building. Along with the continuous insulation, we have continuous air tightness. And this is really, it can seem counterintuitive, and we can use natural ventilation, but we want to start with an airtight environment. We want to have control of it. And if we have control of the air, then we can much more readily and efficiently guarantee the quality of that indoor air. If it's a nice day, you can open up the windows and let the breeze blow through. But if there's a lot of pollution out and God forbid there's a forest fire, smoke headed your way, you want to be able to lock down the building. Mike Horgan had a great analogy that I hadn't heard before. He's like the passive house and the windows are kind of like the car. On a nice day, you're driving down the highway, you have the windows open, you're putting your hand in the breeze, really nice. But if it's freezing out or boiling out, you want those windows to be shut on the car and you want to stay comfortable inside. So we want the building to act a bit like that. So these high performance windows, doors are often triple glazed. They're triple gasketed for air tightness, and they're really thought of as continuations of the insulation layer as well as the air tightness layer. So they're operable. They can be certainly code will require them to be operable. We want operability. We want occupants to have control over their environments. So when it is a nice day, they can utilize that natural ventilation. We also want solar protection with those windows. We do not want to overglaze. We want to manage the sun exposure. We want to minimize overheating, and we'll talk about that a good bit coming forward here today. And then finally, with these first four are all enclosure driven, right? The one mechanical system that's part of the five principles is the ventilation. We'll talk about that at length. So the ventilation is going to have high efficiency heat recovery. It's going to be running 24/7, supplying fresh air continuously to the served spaces, the bedrooms, offices, classrooms, living rooms, and exhausting from the service spaces, the utilities, the bathrooms, hallways. However, you set it up so that you have complete ventilation. We're not relying on a leaky enclosure. We are not relying on weather pressure differences. We are maintaining predictable indoor air quality. That heat recovery ventilation is going to allow us to do it very energy efficiently. With those five things, then, we've really made an efficient building. And then we want to right size the heating and cooling systems. And this is where we'll be headed. So we're often seeing like a 75% reduction, size reduction, and we can have a more efficient distribution. We don't need, because of those windows are so good, we don't need perimeter heating and cooling typically. We can pull it back to the core of the building. So our distribution networks can be smaller, and it allows us with the lower loads, big opportunity to electrify and simplify in some ways there. So all of this is going into our energy model. We're calculating all these five aspects of it, the parts and pieces, the components, the architecture of it. And the key thing here is that we need to calculate predictable performance. This again speaks to the mechanicals in that we want to be sure that we can reduce those mechanical systems. So that townhouse I did in Brooklyn, all the other townhouses similar to that one installed 12 to 15 tons of air conditioning, just standard kind of rule of thumb based on that building type. We did the calculations with Passive House and the PHPP, and we came up with 3 tons of air conditioning for the heating and cooling to a heat pump system. And that's dramatic, right? And when you have somebody spending a lot of money on a home, on a renovation, and you're reducing the mechanical systems that much, you better be sure that it's predictable. And so all the parts and pieces are going into this energy model and is coming back out again, coming in from the specs and drawings and of the design, and then coming back out to the construction site, right? And realizing that in construction. So along with this, we've got the energy balance and we've got it super energy efficient. We can see typically like a 90% reduction in heating energy demand in particular. And there are a bunch of reasons why heating is really the critical kind of bellwether metric. But we are also juggling this idea of electrification, of renewable energy, and where are we going with that? And the mechanical systems that are using these power sources. And we have the carbon emissions, the worry about climate change, mitigation as well as adaptation. So in the kind of traditional model, I guess, we're looking at the carbon emissions from our coal burning power plants, from our gas burning power plants that are driving the electric system, or we're burning the fossil fuels on site. And we have a certain amount of emissions. And we want to put a ceiling on those as well as the efficiency of the heating and cooling. But as we're moving towards a renewable future, is emissions really the metric to measure by? Because we've got, if this is all solar panels instead of coal burning power plants, like how do we know this net zero ASHRAE headquarters is really like optimized or not? Is it really efficient? And what Passive House has done is said, wait a second, as we shift now to a future that's going to be all electric and all renewable, if in fits and starts as we go, we need another way of analyzing this. And so we look beyond this. You can still do this analysis within Passive House, and it's certainly part of it. But the key thing, which ties to our mechanical systems, is this idea of renewable primary energy. And, all this renewable mix, what we're using as final energy at the end of the day, and then the losses that are going to happen, either short-term losses or much larger long-term losses. And how we use that energy, to what extent and when we use it, is going to kind of determine how optimized we are. And really what we're trying to do is use the energy when it's being made, right? The simultaneity of it. We want to minimize the storage and the storage losses of it. And it reveals like a conundrum or a slight problem that we don't typically address, is that, in our net zero paradigm that we often talk about, we may be producing as much electricity as we're using over the course of a year, but we're not producing it at the times we necessarily need it. And so a typical net zero single family home may be producing a ton of energy in the summertime, but its peak loads are often in the winter, and you have this huge gap. And so this requires long-term storage to actually shift the power that you're generating to when you need to use it. And consequently, there's losses associated with that. So you have to produce even more power to make up for those losses. Passive House says, let's tune the demand to the supply. And so if we can crush this wintertime peak, so driven by the heating demand, we can really lower this gap. We can lower the overall production. We're not going to get rid of it entirely. Typically, I mean, it would not typically be reasonable, because then you're making it out of proportion again. This, we want to just optimize those um, uh, supply and demand flows. What load calculation method is Passive House using? I'm not sure what you mean by that. I mean, we're using the Passive House planning package, so it is using, the design temperatures for the coldest, quote unquote, coldest design temperatures and the hottest for heating and cooling and all the parts and pieces of the enclosure. Maybe we can put a pin in that and come around to it later. Or I don't know if Tad want to put in a comment, maybe able to speak specifically to it. But it is, I think it's the math is going to be pretty simple in terms of um, uh, the parts and pieces, the opaque elements, the translucent elements, and yeah. So it's not through manual J. Right. So the load, I mean, you may use those to check back against. And Tad, you could also speak to this perhaps, but in terms of the calculation, it's a good question. Um, uh, the the Passive House planning package is giving you the loads that you're judging the certification on. But you would still depending on the situation, you may refer to the manual J. Absolutely. So what this ends up doing with this new approach to how our systems are utilizing the energy supply is we're looking at use-specific aspects, climate-specific aspects, site-specific aspects in terms of production and in terms of how we're assessing this balance of supply and demand. I'm not going to go into this in too much detail here. We'll kind of weave it in a number of different ways. So we have these different use categories and systems that are going along with them, and they have different relationships to the environment. Some, like the hot water and the electricity, are kind of bouncing along and aren't seasonal, right? But you have dehumidification seasonally, cooling seasonally, heating seasonally. And so the relationship to the supply is going to be different. And we also have load shifting that's potentially that is possible because of the thermal resilience. We can use the cooling or the heating in off-peak hours, and the building will carry through the peak hours. So it really helps with shaving peak if the utility is managing that. We see the load here in January where we don't have enough renewables and you need long-term storage. But in the summertime, there's more than enough, and there's no shortage of short-term storage. Let's keep rolling through this. I don't want to get too bogged down here, but it's all about tuning and understanding the systems to this new reality where we have hydro, we have wind, we have solar, and the different areas are going to be balanced in different ways. And so you end up with these factors for using different aspects based on the location that is helping you judge the optimization of your building. And essentially what ends up happening is that where traditionally fuel oil, natural gas, performed better in terms of a performance ratio to electricity in terms of the emissions. As we move to this primary energy renewable or renewable primary energy, the electricity grid is actually looking better than the fossil fuel use. At the end of the day, what this means is that under the old metric, which is in the red, so the red dotted line is the limit and the bar is the demand. This home in Berkeley, California, if they were using a gas furnace, under the old way that Passive House was looking at this, it would be way under the limit and it would be easy peasy to certify with. In the new way, where the primary energy renewable limit is here, suddenly it doesn't pass muster and you are being penalized for this. Also with direct electric, they're both struggling to get under their limits. But if we move to electric heat pump, now the primary energy renewable is showing to meet the requirements easily, as does the PE demand, but more handily. So there's a preference there. Or I'm sorry, the PE does not meet is breaking through the primary energy renewable limit. On the supply side, so in terms of systems, the solar systems, looking to this idea of net zero, and are we doing it based on square footage of the building? And are we just trying to zero it out? So here we have a low slung building with lots of solar going around the property. But what happens when we have a tall building? You're being penalized. So what Passive House is doing is grading the use of solar power against the footprint of the building and not the floor area of the building. So Passive House is asking us to step away from the mindset of net zero, which can be a little hard to do. Yeah, and deliver this building in a more balanced way. So what do I mean by that? So we can have a tall building, and if we're utilizing that footprint of the building well with renewables, it's going to get a good grade. It's well optimized. It's not counting all the floors for that. So here's some of the background for this. In the mechanical systems, as we shift from the enclosure, the ventilation is the driver of the, I'm sorry, the ventilation is the one aspect of the mechanical systems that is in those 5 principles, right? And then we have the heating, cooling, and domestic hot water outside of it. So this is the focus of it. And then the related energy requirements to that and spelled out in the criteria. So I guess the point here is that mechanical systems, to one degree or another, have kind of been celebrated. The buildings, the architecture has been really about the mechanical systems, and it can still be perhaps. But Passive House is really asking us to check that and going after these basic qualities and looking at the energy and how we're tuning the mechanical systems. We do have these limits. So here are the basic passive house criteria, which we'll look at, is the 4.75 kilobtus per square foot per year heating demand. And then we have a cooling demand that allows a variability for dehumidification. We have an absolute air tightness limit, which is very important, and to delivering everything else. And then this limit to the overall energy use that is based on the renewable primary energy. So this energy use is taking into account that whole kind of universe of renewable energy, storage losses, and tuning to the grid. At the end of the day, what are the typical systems for a passive house? We are, it's kind of boring. We're going to go through some interesting side parts of this, but we're looking at heat pumps for doing the heating and cooling. Makes sense, right? The dehumidification typically. If you're in a hot, humid climate, you may need dedicated dehumidification, but it's often through the heating and cooling. Domestic hot water is going to heat pumps, and the other electric uses we can see here for the use. So in terms of passive house and the mechanical systems, the key aspect is the ventilation goes under the microscope for this. It's a core principle. It's a core driver of the performance of the building in terms of comfort and efficiency. Obviously, the heating and cooling do that as well, but they come after, right? So core passive house principle, extensive certification requirements. Commissioning is key to certification. The attitude of passive house towards the rest is, yes, we have to do it well. It needs to be thoughtful. It needs to be integrated. It needs to be efficient and optimized. But, there are many fewer hard rules. It's really about general efficiency. Any type of system is possible, and you can use fossil fuels. There's no ban on that. The idea is generally with the mechanical systems is to keep it simple. Make sure it's right sized, get it small enough. And that can be a trick. Combining the heating and cooling systems is often happening because of the heat pump. And if you have refrigerant lines and split systems, we want to minimize those. In the domestic hot water size, we're efficient, minimizing circulation, well insulated. We'll get into all of this. Really, the efficiency of any motors, of the pumps, and wastewater heat recovery is encouraged. Again, with the appliances, is about efficiency. I would say really the bottom line is what exemplifies the overall approach or attitude is you've created this passive vessel to deliver performance. And now we want the mechanical systems to complement it. We don't want it to do any harm, especially in terms of accidental heating or cooling. So you have domestic hot water running through, for example, and that is providing heating if we're not insulating those pipes heating it unnecessarily and driving up cooling requirements. So really making sure that we're only using what we need and placing it and having control over that. On the smart systems and renewable systems, again, simple, keep it simple. You can do smart systems, but it's not meant to be driven that way. We want the systems to enhance high performance, not compensate for poor performance. And the renewables, much more balanced, as we've discussed. So in terms of strategy, right sizing cannot be um, emphasized enough. We cannot have systems short circuiting, and uh, um, this is really one of the fundamental aspects of it. Everything we're kind of taking into account with this, the appliances, the population, the use, to make sure that the systems are in balance. One of the biggest problems that we see in Passive House is that the mechanical systems, because they aren't in the core aspect of what we're doing, and it tends to be the habit of architects in general. I can say that as an architect, or as a former practicing architect, we don't give the mechanical systems their due up front. And so this is speaking to multifamily in particular, but it goes as much to single family and other types of buildings as well, that we need to give them their due up front. We can't ignore the space requirements of them, and the planning is absolutely essential. So for efficient layouts, for efficient ductwork layouts in particular. This is a great image showing the ventilation layout, where you have the system and the exhaust ducts in red, the supply ducts in green and blue. In the residential, they're often this kind of flexible ducts, pretty much home runs to a manifold near the unit, and to the various outlets. This is more stuff than you would typically have in a residential project. It's not insurmountable at all, but making the planning for that is essential. A lot of this, like the approach to building science of Passive House, like it's basic in a way. No matter how much we drill down, it's true across the approach, the strategies to building. And so compact layouts, right, are going to be more efficient in terms of systems, in terms of cost and performance, typically. So in the certification process and going through a project development and execution, the mechanical systems, like the 4 enclosure elements, need to be integrated from day one into the planning of it. And we need to do it at that pre-design and planning. This cannot be, oh, we'll get to the mechanical systems down the road. We want it. Passive House really helps kind of good hygiene and good protocol across the board, because to optimize the building, and not just design wise, but cost wise and performance, you need to tackle everything. So getting all the assumptions on board for the different systems up front, running that early energy model and schematic design and design development, where you've got specifications and you've got sizing of systems, as we're going into design development. And before we cross over into construction, we want to create a complete enough set, the construction documents, specifications, the drawings, to an extent, with the energy model, with the PHPP, with the mechanical systems components in it, so that the building certifier can review it and can determine that based on the proposed building that's going to be bid and built, if it is executed, it will be certifiable. It will actually hit that predictable performance goals. And so the I mean, it's slightly different, but it really, I think, can be helpful. It forces you to think about and engage and not kick the can down the road. And so you're making decisions, and when you enter construction, you're really setting yourself up for success. In terms of Passive House and the mechanical systems, you'll see here, I mean, so the as-built PHPP, things are adjusted in the energy model. We are doing photo documentation of all the components, mechanical systems, or representational photographs of the various aspects of construction. We need to do that blower door test because the air tightness is absolutely critical. But then with the mechanical systems, it's really the ventilation system that we are locking down for certification that is commissioned and reported out to make sure that we're going to have that indoor air quality as kind of like the baseline performance. And then the builder is attesting to having completed everything as planned. So, what's not required for certification is the sign-offs on the heating, cooling, and hot water systems in some technical installation aspects. What is required, and we'll take a look at this, are certain aspects around it, the installation of it, the how they affect the quality of life of occupants. So yeah, this idea of being grid friendly. So let's dive into the ventilation. And to be honest, the ventilation is as we've pointed out, ventilation is the one of the main principles and is the key thing that we'll zero in on here. So we have an airtight enclosure. We want to keep the outdoor pollution out. We want to be able to control the indoor air. And if we don't have good ventilation, if we are relying on opening and closing windows, the indoor air quality can get horrendous over the course of a day. And we can have students being lethargic and falling asleep. We have poor health outcomes of all sorts. What happens where we have a passive house control over that interior environment is we have very steady, if not flat, in this diagram, good indoor air quality below 1,000 parts per million. Where in this graph, you see the 1,000 parts per million here. It's going up over 5,000. Key aspect of, how is this air going to move through the space, whether if it's part of a bigger building or a single family home. So the units, we have on the exterior of the building, the outdoor intake, the fresh air coming in, going through the heat recovery core and being supplied as conditioned air. There are two fans, one on the supply side and one on the exhaust side, and there are filters, one on the supply side and one on the exhaust side. We'll go into that. Key thing with the mechanical system, with the ventilation specifically, is that if the ventilation unit is within the conditioned space within the home, the ducts going to the outside are exterior. That unit is essentially exterior. The air, once it comes out of the heat exchange, is interior, but we really need to have control of this. We want this unit to be as close to the exterior as possible. If the unit's outside, this is also outside. And again, there are losses associated with the ducts to the outside, and we want to minimize those runs. But this is a more consequential aspect, perhaps, in terms of potential um, for damages if it's not installed properly. So we can be centralized or decentralized, pretty straightforward compartmentalization. Um, it's important to note the Passive House is concerned with these systems in a way that American manufacturing and industry has not been with the noise associated with them. Passive houses are known to be very quiet. It's not only thermally quiet because the surfaces, that glass surface and the walls around you, the ceiling and the floor, they're all pretty close in temperature. And so you walk into a passive house and you're like, oh, something's different here. But it's not just the thermal quietness of it, it's the acoustic quietness of it. And because that air tightness, the triple glazing, um, we're keeping the outside noise at bay to a great extent. You don't hear the highway, you don't hear the horns as you would. Of course, you can open up the windows and hear all that. But that mechanical equipment that's within the house, within the building, we want that to be quiet as well. And we also want voices from room to room to not necessarily be carried through the ductwork. So we're looking at supply air noise level limits for both residential and non-residential. And then for that quality, the filtering of the fresh air, we want it on the supply side to have MERV 13 minimum, and on the exhaust side, it could be lower to MERV 6. We can see higher filtrations, and we see in smoke areas where people have done supplemental filtration. But it does have a basic requirement of a MERV 13 air filter. You can see here, these ducts are going to the outside, supply and exhaust. So they're insulated and they're going to be well buttoned up. So we don't have condensation issues. On the interior side, the supply and the exhaust extract is uninsulated, right? Because it is essentially at the room temperature at that point. It's gone through that heat exchange. There are other aspects to this. The heat recovery needs to be greater than 75%. The certified units now can have heat recovery over 90%. We want power efficiency of the fan. That's quite good. I think the 2025 California code actually has a higher level of efficiency on the fan power, 0.6. Yeah, supplying that air close enough to the design temperatures on a winter day. Boom, boom, boom. This last bullet point is an important new item, and that is that supply and exhaust air coming into the building to the unit and out of the unit to the exterior, it needs to be within 10% of each other. The units need to be balanced, and we'll talk about that a bit in the commissioning. We don't want to pressurize or depressurize the building. We want the air to get to where it needs to be, and we want it to be done efficiently. This is the typical sort of residential ERV, HRV, depending on the need. And you have these manifolds and a lot of home runs to the different spaces. This could be done in multifamily as well. We'll talk about that in a second. The larger units, it's typically going to be ducted, and you're going to have risers and a lot more complications. We'll talk about that in a moment too. One of those aspects is pulling the systems back to the core, which is very attractive in terms of simplifying things and lowering costs. But we still want to make sure the air gets everywhere with the ventilation. So typically utilizing something of the Coanda effect, where we're bringing that air in close enough to the ceiling surface so it's actually using that surface to throw the air across the room. So it's the same low flow, but rather and to be able to do it at a low speed. The ventilation rates are typically quite low, 20 CFM. It's not air conditioning. And as it goes out, it can then kick the air across the room. It's important when we're considering the ventilation to make sure that it is getting everywhere and we're planning it in a way. We don't necessarily need to supply air or exhaust air from, every space necessarily. We do need to supply it like 2 bedrooms to a living area, but if we're supplying it to a hallway on one side of the living area and you've got exhaust at the bathrooms on the other side of the living area and it's going to move through that space, we want to utilize cascade ventilation or that effect of moving air through the building to optimize the design, the layout. And the key part then is if we aren't supplying everywhere, we need to make sure that it has a pathway. The air can't be stuck and we can't compartmentalize the space. So if you need to compartmentalize, we're going to need to have supply and extract in the same place. But we can do it architecturally and with undercuts around frames. Could use something of a transfer duct within the assembly or have a more traditional transfer duct. Another aspect is to avoid short circuiting, that we've got the supply air coming in, and we need to have enough distance. These are both a supply and exhaust in the same room. Not that far apart, but this is too tight. We've seen this before, where the outlets are put in locations that are going to be covered by furniture and are going to hamper the airflow. So a lot of aspects to executing to make sure that it's done well. One key aspect, and again, it's the basics, but to make sure that we're labeling the pipes. So many, not so many, but certainly on some projects, there will be the misapplied pipe and a supply becomes a return or vice versa, or it's not getting the right airflows. Eliminating crosstalk can be very important, and there are specialized mufflers. We certainly know in transfer ducts, we can have acoustic insulation. We want to be sure if we have a ducted system, in particular with hard ducts, that we are avoiding unnecessary, acoustic interference from room to room. It's also from the mechanical systems. Typically, we're using a recirculating hood above the stove, induction cooktop, electric cooktop, typically. And the exhaust for the ventilation system in the kitchen is far enough away from the stove that it's not getting the grease, and it will ventilate the space. We can obviously use natural ventilation as well if we need to purge. But this setup is quite typical. What's not as typical can happen is uh, doing a traditional gas stove. You can do it with a higher powered hood. And, it's one of these things where there are a number of things that make doing passive house easier or harder. And you can do some of the things that make it harder, but you can't do too many or it doesn't work. So you kind of need to take your pick. And so this is one that some folks will choose because they can't get away from their high-powered gas stove. And they have a hood that is pure exhaust, but the volumes are such that they need to have makeup air and preheat, and it needs to be interconnected and switched, and it's complicated. It's not recommended, uh, but it's not prohibited. It just needs to be figured out. Another thing the ventilation can do is use, and the systems can come with a ground source heating connection. And so in this home, wrapping the building with piping and providing tempered air to that ventilation system. This is a project, a home in northern British Columbia. And so we could take advantage of a bunch of the different technologies. All right, let me move along here. Centralized systems. So another kind of animal, perhaps, but all the same principles. The big thing, we're typically going to have big units either on the roof or on a lower roof or next to the building or in it can be interior space, but often on the roofs. You've got these big risers and long duct runs. Passive House does not require you to test the duct leakage. But it recommends that there be no more than 2% leakage maximum because we need to make sure that air is getting to where it needs to be. It's much more straightforward in a single family home, but when you get to bigger buildings, it's far more complicated. In a single family home, it's almost plug and play. If you have a good layout and you have those flexible tubes and the number of outlets, there's some adjusting to do, but there aren't anywhere near as many variables. With this, the standard practices could end up with as much or more than 30% leakage. And all of a sudden, we've seen projects in larger buildings where there's so much duct leakage that they can't get the ventilation numbers. They have to crank up the ventilation. So then they have much higher energy losses, and it throws the whole energy balance out of whack. And it can be a very serious problem. So making sure, like the building enclosure is airtight, we want the ventilation ductwork to be as carefully airtight practically. And we'll talk about a strategy to do that in a moment. The other aspect is it can be much tougher to balance the systems and maintain airflows. So things like a constant airflow register are quite typically used, where we have ducts and it's not, again, kind of like its own thing per se, as it's coming into contact with the interior construction here, and you have these parts and pieces where the air could actually be leaking back into the construction and not getting to the space. There becomes a requirement of quite good care and practice to make sure that those are all sealed as well. What we do ultimately, it's the one product recommendation, I believe, that know about, and I don't think there's any competitors yet. is the AeroSeal for duct air tightness. They should still be using traditional duct sealing techniques to get it up to, as tight as they can, but then use that AeroSeal to top it off. Know that you've got the tightness down. You're going to be able to hit the numbers at the end of the day. Nobody wants to rip open the building. You're testing the big systems too may have, monitors saying, oh, it's doing this, it's doing that. Passivhaus requires physical measurement at the exhaust and the intake of the exterior to the exterior to know that we're within that 10% of each other. One aspect is we want to essentially oversize the ventilation system. We want it to run at half capacity. It will allow it to run most efficiently, and it will allow for any new needs for boost. It will also allow for potential leakages that are happening to be able to overcome them. You don't want to run out of capacity, and you don't want it to be running at a relatively high rate all the time for efficiency, both in heat recovery and energy use. You go bigger, let it run at a nice, comfortable trot. One of the quirky things with ventilation, when we're going to unitized systems in a multifamily situation, like in your studios, or this is almost like a dormitory, it looks like, layout, where you've got the units tucked in against the ceiling near the exterior, which is good. And you've got the supplies here and then the exhaust of these two coming together. So the supplies and the exhausts are grouped, but then you've got like these long duct runs back. It's taking up a lot of space, softening a big impact on the architecture and the space and the construction. You could also go to something that's more like a single family home model that may be a bit more compact and put it at the perimeter of the building. Again, illustrating it's not bad with the connection to the outside here, but and then it's coming back to the interior. We're softening. Folks like to do this depending on the ownership, just to let everything run apartment by apartment. But then you've got to make sure that all those units are having their filters changed and that there's maintenance and that the occupants are not tampering with the unit. I would say another recommendation is to, if you're dealing with a multifamily, is to typically going to be to go to a centralized unit for the purposes of long-term maintenance and performance, despite the compelling reasons to go to decentralized, because people want their own thing. The checklist for the inspections in ventilation is pretty, straightforward in terms of identifying the specifications, the manufacturer model and whatnot, that things are connected properly. It's photographed. If the sound attenuation devices are specified, that they're installed, that there's condensate drain present, that they're free of dust and debris. There is a rather more extensive checklist. There's a report for the balancing in the commissioning report. I'm not going to go into all of this, but we are measuring all of these supplies and exhausts, and we need to get that report that is showing that we're hitting the numbers and that all the supplies and, well, not adding them up per se, but at the unit, at the fresh air and exhaust, we are measuring those volumes. And here we see it within 1% of each other, which is fabulous. And that's what we want to see. So this kind of report is being issued. The ventilation units and accessories. So this is part of that that manufacturers directory that's on our site. Here's a range of manufacturers, a number providing certified components. Some aren't, but are compatible, and definitely encourage you all to check them all out. All right. Heating and cooling. So that's, the ventilation, it can't be overstated. The importance of locking that down. It is simple in some ways, but it's really in the DNA in terms of providing that indoor air quality is essential. The heating and cooling systems, like we said, it's about right sizing. We're dramatically reducing them. We're pulling them typically towards the core of the building. Not always the case. We are typically using heat pumps. It's typically going to be air source heat pumps. There may be ground source, which we're seeing more of, especially in bigger buildings. Water source almost never, but it does exist in more complicated system. So, we have the mini splits, which we're all pretty familiar with the cassettes. It could be a multi-zone, multi-split type of unit from 1.5 to 4 tons, and then bigger VRF systems. What I wanted to show here, so these two in the middle are typical residential, where we've got kind of a multi-zone system. It could be set, it could be a wall mounted, kind of like a radiator in the ceiling. We could have a heat exchange unit in the ceiling and have it ducted to the various rooms. In the multifamily, in these three, we actually have a growing usage of through wall units, kind of the package terminal heat pump units here, and which are being established at Passive House air tightness, Passive House performance levels. I don't think any is certified yet, but they are going into Passive House buildings, and they do allow for this unitized multifamily approach to that. VRF systems, very common in big multifamily, and then ground source heat pumps in multifamily as well. I don't think we need to go through this too much here. Basic heat pump technology. So in single family, this is kind of the setup between the different systems. In multifamily, it could be, in a smaller multifamily, you could basically have a bunch of split systems, right? All of this is very standard in terms of construction and execution in a way. It's just applying it to the passive house situation. In addition to the ground loop, you could also have electric uh, supplemental heat on the heat recovery unit. We could also supply specific heat to different areas. So it's not unusual to apply some specific heat to the bathroom. So here they're doing a little bit of radiant floor. Typically, we'll see a towel heater, or often see a towel heater in a bathroom to just be able to bump that heat level a little bit higher than the rest of the building. Passive house can operate at a slightly lower temperature than you might typically do, and have the same level of comfort because of the thermal quietness of the building. It just is it allows for easier thermal comfort. Now there may be some debate about this in the passive house world, but I am going to make the argument that um, there are some, maybe cowboy is the wrong word, but some people who want to innovate and push things and figure out things in different ways. And one of the ways we see that happening is this idea of we've got a cooling heating system with the heat pumps, and it could be ducted, and we've got this ventilation system. And the ventilation system is the one new thing that's got all these crazy spaghetti-like pipes going through the space. Can't we just combine them and make them work together? The problem is the system for the heating and cooling needs to run at much higher fan power, bigger ducts, bigger flows, and the ventilation is very low flow, very low fan power. It's kind of apples and oranges, very much so. And so the you know the the basic approach is to keep these things separate. That if you are combining them, you are just introducing a whole set of variables and complications to it, so that the balancing can become very difficult, that there can be a substantial energy penalty, and more wear and tear on the equipment. So again, passive house pushing towards simplicity in what we're trying to do. Domestic hot water. So we are moving towards electrification of domestic hot water. It's the one thing probably in passive house, like much of general construction, that is the last thing being electrified, just because the equipment really hasn't been there. Typically using natural gas, often, although it is now accelerating to heat pump hot water heaters. The big thing we go back to again and again, and it's like a mantra with these things, is minimizing the piping runs and insulating them well. We do not want the heat that's going out of your shower head to be heating up the whole house all year round, 24/7. It's problematic, right? So, the reducing the use is largely dependent on occupants, but that system can make the layout can make a big difference. Some of the obvious things, perhaps obvious, low flow devices, smaller diameter pipes. Using heat recovery is not a passive house mandated thing in any way, but it is credited. You can put it into the energy model And so it is encouraged if we can effectively do that. We show some examples as well as solar thermal. This is where Passive House goes a bit crazy with the not crazy, but um, rigorous crazy with the piping of the domestic hot water. Like we really want this to be continuously insulated, those hot water pipes in particular. No breaks. We don't want the hangers to be breaking the insulation. We don't want uh, uh, any interruptions as much as possible. So you see nice clean. There are even, probably cuffs that can go around this aspect of the pump. Uh, the pumps can be a big issue with energy demand in Passive House and what the assumptions are in the PHPP. So especially where you have recirculation, to make sure that the specifications are meeting expectations. So with the domestic hot water in a single family, we're seeing going to heat pumps, right? And we're dealing with this, and California is mandating it. I think I mentioned this in the next slide for prescriptive path. But if you're doing performance, which Passive House would be, you could still use fossil fuels. So we have a split system where you can have the outside unit and the inside tank, or you have a single unit. The trick is going to be we really don't want the cool we don't want the hot water heater cooling the interior environment. It's much better to be ducting the intake air and the exhaust air and keeping the space isolated and keeping those ducts insulated. It's also a big noise issue, but you certainly can do it. And I do have a slide from the 2025 mandatory requirements that in prescriptive, all the hot water heaters are going to be heat pump in California. And it's only in the performance where you can do gas, but you need to be uh, ready for the heat pump water heaters in the performance path. Yeah. So it's not so much a Passive House thing that for much of the mechanicals, it is just getting it to work as it would for any building. I think Passive House is just a bit more sensitive. So where this heat pump water heater is removing the hot air from the space and cooling it, it's going to be more sensitive to this. And because the space is quieter, you're going to be more sensitive to the noise of the system. So it's going to make you want to plan for that more effectively. In the centralized systems, we can do gas, we can do electric as well, heat pump, which we'll talk about in 1 second. The recirculation, again, the layout, the insulation. Here's an example of a conventional layout for a high-rise building or a tall building, and all the piping that's involved and how they simplified this into a box design. Eliminated a lot of piping, eliminated installation costs, eliminated a lot of heat losses from the hot water, and as such, lessened the cooling demand required in the cooling season. And even for that matter, in through the winter months, you don't want that extra heat being thrown out. You need control of space. Multifamily could be decentralized, like we showed the residential units for the ventilation in a multifamily building. You could do this, and it has been done um, with the hot water as well. Here they are throwing that cool air into the corridor. Um, and in this instance, what they tried to do, and this is the minimizing the tenant interference with the equipment, is to not actually have the equipment accessible from the unit. It's accessible from the corridor. So the building maintenance can access each of these hot water units. Air source is becoming more and more available, and we see it with Mitsubishi. Um, uh, what is it? Heat 2.0, the name of their system, as well as we see Ice Hair here. With the domestic hot water, this wastewater heat recovery could be done in a couple of ways. This Piranha system by Shark is a heat pump system. More sophisticated for bigger buildings. And then we have a much simpler, just gravity thermodrain heat recovery system. And they can be quite effective in terms of minimizing those losses and getting this heat transferred back into either the hot water tank, or it could go into the cold water feed to the shower fixture, for example. So it's preheated in that way. Finally, here with the hot water, big thing, as we're using more and more heat pumps, we need more hot water tanks because of the capacity, and when we're talking about multifamily buildings. So really a matter of, the space for that, the structure for that, and the planning for that, to make sure that it's one of those things early on. What is our system? Where is this equipment going? Make sure we're not stuck. Here are the number of manufacturers. This may be the least populated segment, so open to suggestions. I know there are some obvious ones missing, which we need to get in there, but there are others that could be. Other systems and solar. So just to briefly bring this around. So in the world of electrification, we've got appliances, we've got the ventilation units. I want to note, in the passive house context, and with appliances, the PHPP has standard values here at this upper curve. So it's the least efficient that we've got here, but we can constantly push towards greater efficiency. And it's a reason to, to make sure you get that specification and get the right equipment in. So we have, good appliances and better, best appliances in North America, and then better still in Europe. And hopefully they come here eventually. But definitely it has a huge impact on the energy balance and the ultimate criteria. And we want to nail that stuff down. Cars, another big energy appliance now for our homes, are not calculated in the energy demand of passive house. It is outside of the model, but with that demand reduction, substantially can allow a passive house to effectively deliver free car charging with the solar system. And with the solar systems, we see in the multifamilies, where again we're trying to optimize the footprint of the building, so that these buildings are graded on how they're using the piece of earth that they are covering. We may see carpeted solar like this, but we're not seeing parking lots covered in PV or other park areas. Let the utilities do that. Will be a great building just by utilizing the building area itself. And this ties into in California and the battery energy storage systems and the utilization credit and how that's being enhanced in the new code. And we can have a quite modest system. There's a house in Los Angeles that we'll look at one second. And deliver what the house needs, deliver car charging. This is that house. Quite low heating load. So this is what we're talking about in terms of getting equipment sizing down and the cooling load. It's a fraction of a ton. The equipment tends to be, on the mechanical side, it's off the shelf, really. The basic appliances that we're all getting used to. The induction cooktops are coming on more fast, perhaps in Passive House, but I don't know. It's really the ventilation system that is the unique thing. I don't know if this is equipment or not, but exterior shading, which I've not really gone into all that much, but in terms of, I didn't, and the original principles really dial into it, that, providing the shading necessary to provide unnecessary overheating. We want to minimize the cooling. And exterior shading is the best way to do that. And we don't have a tradition really in contemporary architecture of the last decades of doing this, but we need to figure it out and bring it back. I mean, one of the things that I constantly go back to and people aren't sure, like how, it's expensive, it's an add-on, it's not part of the, my vocabulary, like how are we going to tackle this? I say, let's approach this before central air conditioning was, as if central air conditioning wasn't invented, right? Before World War II, let's say, early 20th century architecture, late 19th century architecture. What is the vernacular? What was the architecture like where people had to stay cool before air conditioning, and use those overhangs, use those eaves, those shutters, those awnings, and shading systems to do that, and think about developing architecture in that way. This is retrofit in California again. Minimal loads, modest solar PV system. The architecture can really be anything. With the equipment with this house, they do have a direct vent hood, but it's not a high-powered one. It's an induction cooktop. So we can throw the system out of balance for a short period of time and not take a huge hit. We'll just calculate that into the energy model. But again, we don't want a huge industrial exhaust hood there without makeup air. We've got indoors, heat pump, hot water heater. There's enough space, there's enough consideration to make that work and not have it interfere with it. Heat pump system, Zehnder, heat recovery, pretty standard stuff, right? And what we see with the results of this house in terms of the energy use, this dark blue line is the average home in that zip code. The blue line was the projected performance of the house. So we see the differential really coming in that peak winter, quote unquote winter, the February, January, December, November uh, months, and tightening in the summer months. But then the actual performance is slightly better still, which is really nice to see. And so being safe, it is a little conservative in a number of ways. So we get the results. The cool thing here is, we talk about net zero and we talk about tuning the building with these systems to an all electric grid, all renewable power. This really is approaching it. If it, the storage losses would be relatively mild here, where we've got the production of the yellow lines below with the monthly average and not huge peaking outside of that. And then the use above the line. The house usage quite a bit below. And then we've got the electric vehicle charging. So that electric vehicle is getting tucked right in to it and is positive. One of the more spectacular buildings that has been electrified is this Hotel Marcel in Connecticut. It's a retrofit of an existing classic modern building, 165 guest rooms, integrated solar. They are putting solar on the parking. They would not have been debited for not doing it. Mitsubishi Heat 20 air source or Heat 2.0. I'm sorry, that's what it said. Heat 2.0 air source heat pumps. Interesting thing is the first Electrolux, first big commercial grade heat pump dryers, clothes dryers that Electrolux brought over to the US from Europe, and an all electric kitchen. So dramatic reduction of energy use here to the hotel from what we see as typical from either mid-size or larger. So that is the end of this presentation, which I just got in under 10 minutes early. There must be other questions or more questions. I know a lot of it was focused on the ventilation system. And because that's really where the game is. But happy to entertain any other questions, discuss anything. What have you got? Anything? We still have most people here, yeah. It appears anyway. Oh, there's a new message. I personally don't have experience with the Apoca units, but I do know they're going into pretty big buildings in New York. And I know they're in the process of going through certification at PHI. I don't know if Tad, you're still on, if you had any intelligence on that with what's happening with PHI and those. I would, so Matt Bowers at Oros Group knows the status. He's working on that, yeah. So they've just entered the market essentially. I have to believe, as a multi, you wouldn't use them in single family. I don't, maybe you could, but I wouldn't, that's certainly not what they're developed for. Um, uh, I wouldn't see why they wouldn't meet California Energy Code. Yeah. ADUs. Yeah. That's a interesting idea and worth asking about. Oh, thank you. It's a lot of stuff. I'm sorry if I'm, you know, it's the first time that we've done this particular subject matter, and um, it's not totally, uh, it's an important aspect of Passive House. We need to, you obviously need to get all these systems right. Um, but it's not in my core fluency as an architect per se. I need to get with some of the mechanical engineers working on these projects. Um, what is Tad saying here? Also, we have growing choice now, smaller home size ERV, Zender, right? Zender and Brink, smaller ERVs than what we're showing in the illustration. There are more and more options, and I think the mechanical systems, the flexibility is really great to see. And as we're electrifying everything, being able to make it all work. Yeah, great, Nelson. We'll see you in the course. Look forward to it. So that's my thank you.
Awesome. Well, thank you, Ken. Do you have our closing slide?
I do.
Okay, awesome. Just a quick reminder for any of you who have questions about Title 24 Part 6, we have a free coach code service online, and you could call a number and they'll answer all the questions you have. Next slide. And just very briefly, I'm gonna launch a poll. Any feedback we could get is always very helpful. It informs what type of classes we bring, and yeah, just any feedback to better tailor our programs. And while you all fill that out, just some quick reminders. Danica Resurreccion was the one who was supposed to be hosting today's training. She was unfortunately sick, but if you have any questions regarding AIA learning units, her email is on the page. Coming to you, we have the slides and the recording. And just a quick reminder, I know a lot of you have been mentioning, but the Certified Passive House Designer and Consultant Pacific Summer Cohort is starting soon, July 1st, I believe. So
Yes.
just a heads up on that. And then we will also have a 5-day passive house design boot camp coming up in September, and then some upcoming classes too. We have July 16 enclosure in detail, and then August 14 intro to passive house trades. I will also put our calendar link in the chat, but it was great having you all. Thank you, Ken, for an amazing training. And if anybody else has any other questions, I'll hang out for a couple minutes. I know we're almost at time, but yeah,
Yeah.
any last questions?
Yeah, me too. I'll hang out. And I just put my email in the chat, ken@passivehousenetwork.org. Feel free to reach out, follow up, and again, I need to give you the final PDF of the presentation, and we can distribute it. Well, thank you, everybody. And we do, yeah. Yeah. Many thoughts in my head right now. When I'm done with these, I'm always like, oh, I'll do this, I'm gonna do that. And
Mhm. Awesome. Well, I don't see any more questions, so I think it's safe to leave now. All
yeah,
right. Thank you, everybody. Thank you, Ken, and I'm
thank
sure we'll
you.
be seeing each other soon.
Yeah, absolutely.
Bye.
Have a great day.
You too. Bye.
Have a good day, everybody. Bye-bye.